Good morning. I hope all these changes won't be a big trouble. Our family has been stuck at home for a long time. Okay, but now I'm in office. I still want to have a good delivery of the lecture, so I come back to the office for this. Um, so today we talk about our tutorial on the surface reconstruction. There's a worksheets in the work bin, so you can actually have a look at that. We talk about two big things today, as in the lecture we suggest. One is the Voronoi diagram reconstruction, restricted DeLonghi triangulation. We'll use a 2D case because I think 3D case is kind of difficult to visualize, but let's use a 2D case to visualize. Then we'll go to the Russell's generation, Russell's surface reconstruction. Okay, so let's start with the surface reconstruction. We'll recap something from Voronoi diagram. That's basically in the lecture. But before that, maybe we can see some Voronoi art. Oh, let's do this first. Okay. So given a set of point, finite set of point in the space, I define the distance measure, which is our normal distance measure. So for all these points, we have made, let's say, n points. For each of the n points, I define a distance measure, which is the normal Euclidean distance. And I want to find the lines of equal distance to both. And that should be our perpendicular bisector. That means the distance to I and distance to J will be the perpendicular bisector of this. And this line will actually divide two states of this one, there's PI and PJ. And this is the line of common distance. However, this will actually divide the space into half. One half is the yellow part, which is more closer to PI. And the other is the rest of this is more closer to PJ. This is the scenario in 2D, which means between 2 points there's one line. Think about what it would be in 3D. 3D will be 2 points, and the separating object will be a plane instead of a line. Okay, so think about that. In 3D, you have 2 points. There will be one perpendicular bisecting plane that separates this point, and would divide the whole space into two half space. And then the intersection of all this will be equal to your Voronoi space. That means I fix a point I, and for I, then actually you iterate all the J points, and we actually intersect all the half space. Then actually that is the Voronoi diagram, Voronoi region of 1 point. Okay, so this Voronoi region will actually contains all the points that is closest to PI. In which this is the demonstration in the class. For example, P1 and P2, this is the two space. One is H12 here, one is H21. If I focus on P1, I don't care about H21 for this moment. And now I have H13, and this H14, and this is H14, and this H15, and this H. So this red region is the intersection of all half spaces. Okay, and then I will just take that out. That will be my Voronoi region of 1 point, which is P1. And I just repeat the things for P2 and P3 and so on, and that's all the Voronoi region. And to construct that, I need to do the DeLonghi triangulation, which is the deal of this. So this is what we talk about. So every point will have an non-empty Voronoi region, and all of the region is convex. You can see that you have 5 points, that each point has its own Voronoi region, and each of them is convex. Even you have an unbounded one. This is an unbounded one here. It's also red, so I cannot see. For example, this one is an unbounded one, which you go all the way to infinity. But they are still convex. And it's unbounded if PI is on the boundary of the convex hull. The intersection of interior of PI is empty if they're not the same. You can see that the intersection of this region and this region, if you just count the interior that doesn't count this line, they will be empty. And all the union will be the whole space. That means, on the other words, you can think in the reverse direction that all the points will be in some Voronoi cell. They must be close to anyone, right? And the de Longley triangulation is whenever you have two Voronoi cells touching each other, you have one convex hull. For example, if you take each Voronoi cell individually, itself intersect itself, right? So that's why the point, you see, become black. All these points are in the de Longley triangulation. And then that is for each single Voronoi region. If you take any two Voronoi region, let's say this one and this one, because they are actually intersecting in this line, and that's why these two Voronoi regions are intersecting each other. If that is the case, I put a line there. Okay, so you can see that P2 and P5 will have a line also, because P2 and P5 actually intersecting here. Okay, this is the intersection of P2 and P5, and so on. But you can see P1 and P5 does not intersect. The region of P1 is this one, the region of P5 is this one, and these two does not intersect each other. And that's why there's no line for P1 and P5. So that is the case for two Voronoi cells intersect each other. And you can see three Voronoi cells can intersect each other. For example, this Voronoi cell here, this Voronoi cell here, and this Voronoi cell here, they both intersect at this point. And that's why P1, P2, P3, I will draw a triangle because of what I said. And you just repeat that. So for example, P1, P2, and P5, definitely you don't have a triangle because P1 actually intersect P2, but P1, P2 does not intersect P5. So, and then you have this de Longley triangulation. So there's a basic construction of de Longley triangulation, but we haven't reached the restricted de Longley triangulation yet. So if you have an underlying surface, I can do the thing, which means I sample some points on the object, and then I construct the Voronoi diagram, and then I construct the de Longley triangulation. So this one I would suggest you to do your exercise yourself, like that. Okay. So this is supposed to be the de Longley triangulation. And now the question is, if I want to compute the restricted de Longley triangulation, how do I determine which of the red edge of the de Longley triangulation has to stay? Okay, so the basic idea is, let me change a nice color. Not this one. The basic idea is, if your de Longley edge, or if your Voronoi cell or de Longley edge is intersecting the diagram, then you keep the edge. For example, this edge here, right? This de Longley edge. One de Longley edge is pairing with one Voronoi edge, which is this one. Okay. So this Voronoi edge is intersecting the surface in one point, and that's why we want to keep this one. However, you can see this edge. This edge is connecting this point and this point. And where is their Voronoi edge? You can go and follow, oh, this is the Voronoi region, and this is the Voronoi region, and their intersecting edge is this one. Does this Voronoi edge intersect the object? The answer is no, because the object is here. And that's why this edge will not be inside. And at the same time, this edge also will not be intersecting the objects. And that's why we will eliminate these two edges. And after all this one will be removed, this one will be removed. And we have a restricted de Longley triangulation like that, in which you see that is not what we want. Because you can see the original topology of the original object is actually a cycle. But now you have an X shape because the red edge created an X shape, which is not what we want. And that goes to what is the importance of keeping the topology consistent. And the reason is that goes to our closed property theorem. You can see that when you take off each of the vulnerable cell, for example, this is one of the vulnerable cell or vulnerable region. Sorry, I keep changing the terminology. Vulnerable cell is a vulnerable region, okay? And when it intersect the surface, is this part. The topological ball properties tell us that you only will keep the topology if every of this intersection is a topological ball. A topological ball means this intersection is one piece or one segment. So in 2D is one line segment. In 3D is one flat surface like a disk. Okay, so this one is okay. For example, this region is okay because it intersects this like a disk. Which one does not intersect the surface like a disk? Which means which vulnerable region is not intersecting the surface in a segment. So you can go and verify. For example, this one intersect one segment. So this one is okay. And this one intersect the vulnerable cell like a segment. So this is also okay. And this one also intersect like a segment. So it's also okay. So what I said is because this vulnerable region is intersect the surface in a segment. So it's okay. So you can see the central part is not okay. Why? So you can see the central part. This is a vulnerable cell. And when it intersect the surface, you intersect here and here. So you can see that within one vulnerable cell, you actually intersect the original surface in two segments. So that's why it destroyed the topological ball property, and that's why it's not valid. Okay, so that means go back to the point is this sampling of the surface is not good enough. Okay, and the question is, how do we make it better? The very normal way is add more points. Okay, so maybe someone suggests where should I add a point or where should I sample more? Maybe I can actually sample here. One more point, okay? So let's see what happens if I sample one more point like that. So I try to draw the vulnerable diagram, okay? So if I sample one more point, the vulnerable diagram may be something like this. Okay, so hand draw vulnerable diagram, okay? So my new vulnerable diagram will be like that. This is the new vulnerable diagram of adding one more point, right? Or I think maybe not very accurate, but somehow it's like that. And when I want to draw the Delaunay triangulation, the edge will be like this. And I have an edge here, I have an edge here, edge here, edge here, edge here. Okay. And now let's see which Delaunay edge is being kept. For example, oh dear. Okay. I need to undo. Okay. For example, you see first this vulnerable edge intersect the surface. So that's why I keep the edge. And that's why this edge I kept. And this also I keep, this I also keep, this I keep, this I keep, and this I keep. Okay. And you can see this edge over here, the corresponding vulnerable edge is this one. But it doesn't intersect the surface. And that's why this edge I don't keep. And for example, you see some of the interior edge, for example, this edge here. the corresponding horizontal edge is this one. And this horizontal edge doesn't intersect the broken line surface, and that's why we also don't keep, and so on. And at last, you see this is all the remaining horizontal edge, and you see it somehow resemble the original objects. And that's how you add one more point, will actually keep it. So the algorithm to reconstruct the surface, if you know the underlying surface formula, will be sampling enough points and construct the restricted de Lorentz triangulation. Okay. So any question on this? You can add more points somewhere. Actually, it may work. So if you add even more points, let's say I add a point here, I add a point here, add a point here, add a point here, add a point here. If more points you add, actually it will actually make it even nicer. Okay. So all about this algorithm is how do you sample enough points. Okay. Any question? And this one for 3D is the same thing. 3D is the same thing such that when you do this, when you have this, each of in 3D, each of this will be a flat surface. And then for a de Lorentz triangulation, you just see if the edge is intersecting the surface, that will be the 3D restricted de Lorentz triangulation. Okay, so that's the first part. Any question? You can try the one on the worksheet, and also you can try the past exam paper. I don't know if I post the past exam paper, but one of the past exam paper actually have one of the exercise of this, so I can actually post it out later for your exam. Okay, if no question, then we'll move to the second part. How do we do reconstruct the surface by visualization? So for any of these field function, that means for the whole space of x, y, z belong to the space, I can actually assign a value. And each of the values, we can decide what is the point of the grid going through. For example, if I think I will, again, this should be 5.5. So okay. So let's say if I want 5.5, let's say this is the on the left side, this one is the field. So this field actually just sample some of the points. Because this is actually a vector field, for any of the points here, I actually have a function. But I don't need to take all of them because it's a continuous surface. So I just need to sample some points. And after I sample this, I can actually say, what is my level set of V is equal to 5.5? Then I have this diagram. This diagram means this is less than 5.5, and this is more than 5.5. So we actually can say that more than 5.5 is equal to the interior. And if you set V to be different values, for example, I want 3.5, then it's actually this line. If I set V is equal to 7.2, then it's this line. Then it will be the only one that is more than 7.2. And these 3 points will be outside of my region. So after that, you will have some type of this black and white dot on the checker box. And how many different combinations of in 2D after eliminating the symmetry? You can think that the number of inside vertex, if it's 0, you have only one case because it's 1 white and 3 blacks. So after you eliminate all the symmetry, you only have one case. Oh, sorry, 0. 0 means all no inside, all outside. Let's say all white. Okay, 1 white is one case. The case that with 2, we have 2 cases. 2 cases, which is you can have 2 black and 2 white. The 2 black can be neighboring to each other or not neighboring to each other. Okay, so if you talk about the arrangement in clockwise order, it can be white, white, black, black. It will be the same as white, black, black, white, because the white and black are neighboring each other. The second case is white, black, white, black. That means when you turn it around, it's alternate. So this one is black and this one is white. And 3 inside and 4 inside, which means 4 black and 3 blacks and 4 blacks, they will be the same. So which one is the ambiguous case? It's quite easy to see, right? So if you have two vertex, that will be the ambiguous case, right? I don't know how to connect them. So if I want to join them, basically I just need to take care of every square. And if the square have only one black and three white, I can actually think that the surface is like that in this portion. And in 3D, it's just more complicated. Okay, so let's try an example. This is a grid. Let's say I want to do these shapes. Okay, this is my surface. And what you do is you just need to label all the points that is inside the surface, which is all this black. Okay, and what will you have if you just take the Warsaw will be this data. Okay, so that's what we got in 2D. The blacks are inside, the whites are outside. So how do you join the surface? You are supposed to join the surface like that. But if you see each of the grid, you just have to take care of each of them. For example, when you talk about this grid, you can see that it's two white and two black. That means your lines must go through like that. Okay, and for example, this one over here, you can actually see that is three blacks and one white. Your lines must be like this. Okay, and this line must be like this, and this line must be like this, and you just have to take care of all the grids. Okay, and if you take care of all of them, then you just have this. So the red line will be so-called the surface reconstruct by this black and white dot. But one thing to take care of course, I can argue that, oh, actually my surface is like that, go through like that. But maybe what happened is, see this, my surface is like that. Okay, which is possible. If you really have the surface like that, you will produce the same black dot and white dot. So the only question is your black dot and white dot samples dense enough? Or the other question is, do you need that density? Because for some application, we don't need to be that dense. Let's say I'm scanning your brain. You may not need this type of density because the density is already big enough. Okay. So if you follow the construction, you have this surface. Let's try this, your time. How to reconstruct this? The black dots are inside, and then the white dot is outside. Let me give you maybe 2 minutes. Anyone try to join in, and you can be distributed. Someone can actually do any part. Anyone, you can annotate. For starter, you can actually do this one. Okay. Anyone? No? Okay, then maybe I'll do it. Okay, so what you do is, this is the certain one I can. So it's actually a TV shape like that, and I actually do this. Okay. Can you see that I left two Warsaws open? Because those are the Warsaws with two black dots and two white dots. And actually, for those Warsaws, I can have more than one case of configured. Okay. For example, these two black dots are inside, right? And the two white dots are outside. I can, like this, in which is a valid configuration. And I can also do like this. Both of them are the same. And that's why I'm talking about the ambiguity of the connection. So in 2D case, there's some ambiguity there, even you make it very simple topology. So the question is which one? If you have this, then how do you connect? Which one is the correct topology? For that, if you just based on the data, you have no way to tell. Okay, is it this one, which makes a bit like a frog? Okay, it's a bit like a frog. And this one is a bit like your TV. Okay, so which one is the topology? And also the bigger question is 3D, how many of them? So 3D will be more ambiguous, okay? 3D will have even a lot more ambiguous. And this thing you cannot just base on the configuration here. So there's some solution that people suggest. One is consistency, which talk about later on the, for example, how do you actually, if you have a surface, how do you actually project onwards? And some of the statistical approach, like how to do neighboring wassels or how about normal vectors, as in you actually take it from the surface. Is this surface actually going down like this? Is more natural on all these normals to proceed on, or is it not? Okay, so there's some, you can actually collect some data on the surface to continue. One is a topological persistent. That means in a simple way, later we'll talk about in the next slide. In a simple way, it means if I want to make the topology more simple, let's say I want to make the whole thing as one piece as possible, then you actually choose this one instead of this one, because this one actually make your whole thing is more like one piece. And of course, you can do deep learning on AI side. Okay, so that's not my area, but I think a lot of people do that. So for persistent algorithm, is actually I try to build the simplex or build the surface as persistent as normal. So what it does is actually you can see what it's actually doing here is for a set of points, you try to build the triangles, which means you add the triangles and edges inside. And the order of adding, I try to make the topology consistent. That means all throughout the flow, I actually try to add every time that I try to maintain one piece. Okay, so that is the use of how to reconstruct this. Okay, from this set of points, how to reconstruct that. And there's more variation of that. For example, can you use other than cubes? Because think about it, the cubes are actually laid on the vector field. And the vector field is actually what we have already, but we can actually lay other than a cube. And because you have a vector field, if your vector field is dense enough, you can actually have adaptive types of wassels. I make it smaller and smaller, even divide it smaller to try to make my surface construct to be more details. And how about more vertex? For example, instead of putting vertex on the boundary, I actually add more vertex inside to make it more smoother. So this is one of the examples. The left ball here is the margin cube. You can see all those vertices aligned to the edge of the cubes, but you can actually add more smoother one to make the ball look nicer. And of course, how do you use this method to construct CSG? So actually this black and white dot will be very easy to be computed by the CSG, as I said in the last tutorial, I think. And can we even fit smooth patches instead of triangles? Okay, so for example, here, instead of fitting polygons, can you actually, each of them is a smooth patch such that the whole surface will be a continuation models, and you don't only fit one patch. Is it possible for a few patch to fit one parametric patch together? So there's an ultimate goal. Okay. Okay. So at last, this is your exercise. Maybe you can try to fit in the surface for this model. Okay. Let's say it's a wassel. So this is the last one. I will leave 1 minute here. If yeah, it's your turn to try. And the question is, which one is the ambiguous one? For example, let's try, for example, this one. This is those quite sure one. Let's say, for example, this is quite sure. Okay. And this one, I will actually project to here, this one here, and this one here. Okay. And this one here, here. And when you meet those square with 2, you may have an ambiguous case. So let's just fill with all those sure case first. Okay, so this one is like that. This one is like that. And then this one is like that. Okay, let's see more. This one. Okay, you can see that I actually fill all the edges. And the question is, all these 2, what do you think? For example, this one, how do I fill it? Should I fill it with this one? Or should I fill with this one? Okay. So from the data itself, I have no way to tell. But if you see that, oh, this one actually is a bit like a teapot, right? So the most logical one is like this. So you can see that the whole thing looks like a teapot. But if you don't know it's a teapot, you can anyhow fill, for example, this one, I can actually fill like that. In which you can see the topology of the whole thing become 2 pieces. And that's where like algorithms like persistent algorithm can work in place. That means I actually try to add those edges such that my topology is more persisting. That means I want to be one space, one piece. For example, it's like that. Okay, then the whole thing is one piece. And that's what the topology persistent means. And in fact, one of the not so good thing about our example is it's a small example. In real example, you have more points, and those points will have less details of like this. And that's why you actually can chase the persistent more. Okay, so this is our tutorial today. Any questions? If no more questions, then what we'll do is we'll actually leave it to next week. So what I will do is I will send out an email. I will tentatively make a slot for everyone. So if you have problem of the slot talking to me, then please let me know. Okay, so the slot will be next Monday. It will be in the same tutorial section. Actually, if you want to talk to me in another time, which is okay, because I think according to NUS, this is the last week. So next week I could have no lesson. So I will do any times on Monday. So I will tentatively schedule a anytime slot. So let me know if you can or cannot doing that. So I will also send out the requirements. I think what I want you to do is to need to write at least send me by email some kind of write up what you want to do and what is the deliverable you want to have. Okay, so please wait for my email, and that's all for today. Okay, so see you soon on the meeting session. See you.